Ferro. I work for PetroVR, and now I will talk about OpenCL in Bee Smalltalk, which is our development platform. This is mainly an experience report, so don't expect great recommendations. We are starting to experiment with the use of OpenCL, and I will tell you what we did and how it resulted. This started with Juan Buletich, who is an old friend of us, which is also the author of Bee Smalltalk. And in a Smalltalk on the corridors of the Smalltalks conference, he told us, you must use OpenCL, it's great. So we took the advice, and the task fell on the shoulders of my wife, Alejandra de Bonis, which made the work of checking the quiz implementation, extracting the interesting parts, reading all the documentation, and then include it in Bee Smalltalk. She should be here presenting this because it's her work, but I think that she wouldn't dare to let me with our daughter for 1 week without supervision. So this started like this. We have hardware, which we are not using much. We have multi-cores in the GPUs, at least 4, and most machines have more. We have graphical adapters and GPUs with many more cores than that, and we don't use them in Smalltalk. And we have this magnificent low-level platform, which is OpenCL from Kronos. So the next step, we need a problem, because we are programmers and we work like this. We need that covered. But not any problem, a problem which makes sense to solve using parallel computing. A problem which can be divided in blocks that we can process in parallel without complications. We have a strong piece of our simulation in PetroVR is the Monte Carlo simulation. And Monte Carlo, since it has lots of iterations, sounds attractive for parallel computing because every iteration represents a different world with null interaction with the rest of the iterations. We express this using multiple uncertainties, which are represented here in these physics model variables that are the uncertainties of our simulation model. We use sampling of those variables, of those uncertainties, according to some distributions, statistic distributions associated to them. With those samples, we build and run the multiple simulation worlds. Here is the number of iterations, which is directly connected to the generation of independent worlds. As I said before, this is attractive for parallel computing, but this is not the kind of parallel computing that we want to do with OpenCL because it's extremely complex. So we have attacked this in the past by distributing the simulation of several iterations in different machines or in different processes on the same machine communicated by sockets. So where can we use OpenCL? We have a final stage, which is the most interesting for our users. After running those simulation worlds, we need to collect and show and analyze the results. What are the results? Well, it's something like this. We have, for single variables up here, we have the name of the variable and several statistics indicators. We have the same for arrays, but in terms of its time series. So many of our results, like oil production, like cash flow, expenditures, and so on, are expressed along periods of time and are an array. So this represents the variation on the result sample of this array around the thick line, which is the average. So this represents the degree of color represents the density of samples in the result around that, in few words. So this requires computing the central moments, the statistic moments, for all the result variables, for all the iterations. We have all the central moments are a variation of this is the distance elevated to some power and summed across all the sample. And also we have the percentiles, which have an interesting statistic meaning, and we calculate for every variable 20 percentiles, every 5%. So this is lots of information that we provide to the final users. And it has this form. For array results, as I said before, we have one value for each period, which are the columns, and we have lots of iterations in the order of hundreds or even thousands on each row. So this builds a large matrix, and on that large matrix we have to calculate column per column the different indicators, the different moments and the percentile. So it's interesting to compute in parallel because no column has anything to do with the other columns. We calculate separately each one. So that is an appropriate match for OpenCL, matrix operations. What is OpenCL? Because many of you may not be aware of this. This is an extract from the documentation. It's too long, let me summarize. It's an open standard for parallel programming which allows us to abstract from the real hardware. So I'm not sure what I have here, but I can use OpenCL here and it makes parallel computer for me. That is great. Besides, let me summarize again, it consists of an API. In our case, since we work in Windows, it's a set of functions that we can call via FFI from the DLL. It has support for a programming language where you express the computations that you want to do on the platform. That programming language is a variant of C, the old C99 standard. And it also has an abstract specification and a comprehensive manual. How does it work? Interesting question. Well, if you know the answer, tell me. Basically, you have the host, which represents the computer. On the computer, you have different platforms. In my case, it's CPU with the Monte Carlo processor and GPU, but you can have more. Each platform has is represented as a compute device and is divided into compute units, which are further divided into processing elements. The processing elements are the interesting part because they are which perform really the parallel operations. This along the hardware part. Now, the problem space, which is usually some matrix, some multidimensional matrix, not many dimensional, multidimensional two-dimensional science fiction. It is one dimension for arrays, two dimensions for matrix, and you can use three-dimensional matrices. But this example is with a two-dimensional matrix. You divide the problem space in work groups, and the work groups are divided in work items, which again are assigned to the processing elements and are processed in parallel. In this case, we have a grid of 4 by 4 processing elements or work items. Every work item is processing the same function on those elements. So the same set of operations are applied to this, to this, to this, to this, and I think you get the idea. In parallel, in the work group, you can specify some relations between work groups that is more complex. You can do this partition by specifying the number of work groups you want to have, but you can also forget it all and let the platform do it for you, which is what we do. This is some UML diagram of the model that also comes from the handbook of OpenCL. And well, it is not very interesting, but I will explain later on our implementation. But almost all of these classes, we have some smaller implementation for them. So let's see the smaller implementation finally. But we all came to see. Sorry, I have some diagrams. I don't like to show much of code because it's hard to read. We started with a main abstraction, which is OpenCL object, which is more or less its handle to an object in external memory. It also knows the OpenCL DLL to call low-level functions from there. And we have some cache of the platforms for not to get them from the low-level call every time. The rest is some default protocol for release, initialization, and finalization. Well, we have several subclasses of these. Where should I start? So I should start with the platform. The platform is the first abstraction that you can see when you start using OpenCL. As I said before, it represents hardware. It has one or more devices. It has some protocol to get the devices and start creating these options. The device is over here. Well, yes, they have not much of an interesting protocol, but they are required to create a context, which is the following object. A context is exactly that, the context where the OpenCL computations are performed. It is associated to one or more devices. It can have some callbacks to tell you what is happening. And it can build a program with the source code. The program time it's like the source code for OpenCL. It knows how to build, which is what we would say compile to an executable bytecode form for OpenCL. So the interesting part of the program is that it can produce the kernels here. The kernel represents an activation of one function of the program, and the kernel is what we will apply to the items from the matrix. This is really executable. You can set the arguments, and then you have the command queue. On the command queue, you can put some commands to run different kernels. This part. These are the commands that you can put on the queue. Are very few. You have a read buffer command, a write buffer command, and this with the long name, which is use this kernel on your input. Well, we have to add some auxiliary classes like this OpenCL error, which is to handle exceptions that come from the OpenCL operation and distinguish them from the normal exceptions. As I said before, we have the DLL, with all the functions from the platform. And we have this additional abstraction, OpenCL matrix, that we have to introduce chat because the float support, we need to be able to support floating operations in single or double precision. So this is mainly to deal with that. Well, now we are approaching to the client side. Those were implementations of how to communicate with OpenCL and use it in the terms that OpenCL proposes. Now, for our model, we don't like that much. We have a layer of abstraction on top of that, which are algorithms. The algorithm has very basic protocol. It's an abstraction that you use since many years. Has a lot of subclasses, but now we added one which is OpenCL algorithm. This OpenCL algorithm has a lot of instance variables, which are the OpenCL objects, and he knows how to create and connect them among themselves to run some specific calculation. Now we have the subclasses. The first subclass that we did as a proof of concept was this, OpenCL column average. That is a very simple calculation which takes a matrix as input and calculates the average of every column. So the output is a one-dimension vector with the averages of the columns of the matrix. It's useful. It was very useful to discover things, issues, problems, and also for testing, because it has a result that is very easy to validate. On the other side, we have the OpenCL statistics algorithm, which is the one that we really use, and it calculates through the other three. It calculates the statistical moments and percentiles and all the indicators that I mentioned before on a matrix of arrays that come from iterations of Monte Carlo. Finally, on the model side, we have the calculators, which are the objects with the Monte Carlo machinery interacts. These are in charge of invoking the algorithm for every array element. Now some source code. Well, as I said before, the programming language supported is C. So our source code is C code. This is the main piece in charge of calculating the indicators. If you see after the large series of initialization and type declaration that we all are relieved not to do, we have the calculations. These are the calculations of the moment, and you can notice that this method has a long source code, but all the operations are very basic, are just elementary math operations. Product, division, it has a low complexity. This is the high-level composition of the source codes of the auxiliary algorithms. And this is another extreme point. This is really complex. It's quicksort. One implementation of quicksort is C. This is absolutely unreadable. Don't even try it. But the reason why we can use it is because it's blessed by the internet, which is our authoritative source for known algorithms. And besides, we do lots of testing to be sure that it sorts accurately. Well, now some results. I have taken measures only of 4 different projects, doing 1,000 or 2,000 of iterations for Monte Carlo. The first one that I want to show is it's called 100 array. You can imagine why. It was authored by our testers to show the specific strength of this. The first 3 are 1,000 iterations. The second block of 3 is 2,000 iterations. And the different columns are the first with no OpenCL, the second with CPU OpenCL, and the third GPU OpenCL. But this is not the, here you cannot appreciate difference, because this is the time to run the Monte Carlo iterations. Now, on top of that, I will add the time to calculate the indicators. In this case, it's 2 times larger than the time to calculate the iteration. So this is an extreme situation, because you run a complex simulation and you run it for 20 minutes. And then, to get the results, you have to wait 40 minutes to complete just the estimator's calculus. This one instead is 100 single results. So here the difference, the time to calculate the estimators is very small compared to the other one. So you don't see any noticeable effect here. But this one, no, this one it's pretty much the same. You have a small blue bar over here, and it has the same extent using OpenCL or not using it. And we have here another example, this time with a customer project, not an artificial one created by us to show the strength, but a real one. And it also shows some interesting effect, because this is without OpenCL and this is with OpenCL. So, back to the presentation. I have some slides. about this just in case. But the final conclusion is, in none of these cases, we got worse performance using OpenCL. So it is safe. We are playing safe by using that. In some cases, we got noticeable performance enhancement, which is nice. And we have to research this last bullet because there is very little difference between CPU and GPU times, which was a bit of unexpected. We have to experience this with other hardware because this notebook is the graphics adapter is not really to do these kind of things. Well, now after the final words, I have a bonus track, and that is in which other parts besides the code that I showed you and the classes that we have to add, which is in charge of the development team, in what other parts of our whole team it has impact. And this is great because it has lots of impact. And that shows us that just writing the code is a small part of doing software. We have to modify documentation because now we have OpenCL capabilities and we can have OpenCL troubles. So we need to add some troubleshooting on the help, some appropriate mentions in the manual and in the installation guide for the final users to be able to get the OpenCL support in place if they don't have it before. The graphical user interface had to be changed because we, even for ourselves, we needed to know when we are using OpenCL or not. Just for things like producing these charts, I needed to know and measure the times of OpenCL operation. So the Monte Carlo GUI had some modifications. The system status now has a section informing the user what OpenCL device would use if there is none, and things like that, some specifications of the platform that is using. And the results report now includes the time spent calculating the estimators. The IT department had to do some research to provide the installation guides for the users and even for the development team about controllers, specific hardware, and so on. The testing team had some interesting work. We had to write some specifications for them about what could or could not find during the tests, and they had to test many cases. And finally, the communication team, because this has to be has to have some kind of marketing. It is pretty much invisible. If I don't tell you, you don't know that I am using OpenCL. So we have to put release notes, write blog posts, write newsletters, produce a movie, which is not a Hollywood production of Avengers versus OpenCL, but some modest how to use what you should see and things like that. And of course, this presentation of the exam. Well, thank you very much. I think my time is over. So if you have questions, you can